Okay, so in this discussion, I'm mainly going to focus on section 10.2. Okay, you need to read through 10.1, look over the molecular orbital theory, and know what it's about. But we're going to talk about the valence bond theory that was developed by Linus Pauling. And basically, it illustrates the overlapping, of atomic orbitals for two atoms. And these are formed when your electrons are localized. And a lot of the reason why this happens is that it allows you to create half-filled orbitals. And by creating half-filled orbitals, you are now able to form a covalent bond. So what will happen is, let's say for instance, you have an element that has one s orbital and one p orbital. And by the one, I'm not talking about energy levels. I'm just talking about it has literally one s orbital and it has one p orbital. And what it does is it creates two sp hybrid orbitals. The s and the p have combined to create an orbital, and you now have two sp hybrid orbitals. And there will be an electron housed in each one of those orbitals. Once you generate these hybrid orbitals, they still fill according to Hund's rule, which means one electron in each orbital, and then they can start pairing up. If an atom has one s orbital and two p orbitals, then we now will generate three sp2 orbitals, one electron being in each one of them. And then so you can follow the trend going down. Now, how do we determine the hybridization? So the first thing I have to look at is how many unshared pairs are on the central atom. Now, can you do this for, say, a terminal atom? Yes. But essentially, if I want to know what type of hybridization is occurring in my central atom that is forming these bonds, then I'm going to focus on the central atom, determine how many unshared pairs are there. And so if you look at the first example for phosphorus, phosphorus has absolutely no unshared pairs. It then has 5 pairs of electrons that are forming single bonds. Because realize once it's bonded to chlorine, it gets to count that electron from chlorine as part of its electrons. So that means that it needs 5 bonding orbitals to make these 5 pairs happen. So it needs one s, 3 p's, and then it's going to need one d, because remember, phosphorus is one of those that can have an expanded octet, which means it can also have extra electrons go into its d orbital. So while phosphorus alone technically only has s and p as part of its valence electrons, we're going to expand it to the d orbital so that these 5 bonds can happen. And so because you need that, it becomes sp3d hybridized. 1s, 3p, 1d, sp3d. So over here on the side, you will notice the 5 sp3d orbitals, and 1 electron goes in each of the 5 orbitals. So that when it then pairs with all 5 of the chlorine atoms, then chlorine's electrons will then occupy 1 in each of those orbitals to generate those 5 bonds. So we have generated 5 half-full orbitals, and we know that half full denotes that you now have A, it's more stable to have half full orbitals, and B, now you can form a covalent bond with something else. So chlorine's atoms are going to come along and now form a covalent bond with all of the free spaces in each of those sp3d orbitals. Okay, then you have pf3. Well, notice that pf3, it has one unshared pair. It has 3 pairs forming single bonds. So it has 4 bonding orbitals that are totally needed. So it's going to be sp3 because it needs 1s and 3p. And that's going to be your hybridization. Now, it now has one that's full. Why is this one full here? because of that lone pair of electrons on phosphorus. So they're already partnered up. And then you have 3 half-full remaining, and those half-full are capable of bonding, and they're going to bond with the fluorine atoms. Over here, for C2H2, we are looking at the carbon atom, each carbon atom individually. So there's 1 pair from the double bond, 2 pair from the single bonds, and by single bonds it's carbon. If we're looking at carbon, we have the double bond to carbon, and then we have 2 single bonds to both hydrogens, so we count both pair. When we do double and triple, we only count them as 1 pair. So a total of 3 are needed, so it would be sp2 hybridized. It would also be sp2 hybridized on the other carbon because it's the same thing. And then, of course, I did the same thing for the C2H2. There are no unshared pair. There's 1 pair from the triple bond and 1 pair from the single bond. So 2 bonding orbitals needed. So you just need 1 s and 1 p, which is sp hybridized. Same thing would happen for the second carbon. The next one for nitrogen, you have 1 unshared pair on each nitrogen, 1 pair for the triple bond, so it's sp hybridized for both nitrogens. And then for F, we're just looking at the nitrogen that is the central atom, and there are 0 unshared pair, 1 pair from the double bond, and then 2 from the single bonds, and so it is sp2 hybridized. So when these clouds overlap, your hybrid orbitals actually form what are called sigma bonds. This is just a head-to-head overlap of your orbitals. And it kind of makes symmetry when this happens. Now your pi orbitals are due to a sideways overlap of your p orbitals. So the electron cloud density is concentrated into actually 2 lobes versus 1. And there's 1 above the axis and 1 below the bond axis. All single bonds are sigma bonds, which means there's a head-to-head overlap for all of them. Double bonds have 1 sigma and 1 pi, so it's one of the bonds will have a head-to-head, the other one will have a sideways overlap. And then for triple bond, there's 1 sigma, so there's 1 head-to-head overlap, and there's 2 pi, so that there are 2 sideways overlaps. So if I look at the first example that it gives, it says give the hybridization a number of sigma and pi bonds. Well, how do I figure out sigma bonds? First thing I look for is single bonds. So I have 2 single bonds, so that's 2 sigma. Then I have a triple bond, but realize that one of the bonds in the triple bond is sigma, so that's where the 3 sigma comes from. Then I have 2 other bonds left over on my triple bond, and both of those are pi bonds, so those are my 2 pi. They are both both carbons are sp hybridized. Why? Because there are no lone pairs, and there's 1 bond for the triple bond and 1 for the single bond, so you just need 2 orbitals, the s, 1s and 1p, which makes sp hybridization. The second one, the O is sp2 hybridized, the N is sp2 hybridized, and the chlorine is sp3 hybridized. There are 2 sigma bonds total, 1 from the bond between N and Cl, and then 1 of the double bonds from N to O is a sigma, and then the second one would be the pi. For SO3, if you draw it out, 2 of the O's are sp3 hybridized, and the O that's double bonded is sp2, and your sulfur is sp2 hybridized. And then you have 3 sigma bonds, 2 from the single bonds, 1 half of the double bond is sigma, and then the second half generates a pi bond. You need to be able to figure out hybridization, and you need to be able to figure out how many sigma and pi bonds are present. Again, make sure that you read through both sections in Chapter 10 to make sure that you understand.